Radioactivity in elements is primarily a result of their atomic structure, specifically the instability of their nuclei. The elements that are most radioactive typically have a high number of protons and neutrons, leading to instability. This instability is what causes these elements to emit radiation as they seek a more stable configuration. The process of radioactive decay can involve the emission of alpha particles, beta particles, or gamma rays, each with its own unique properties and levels of energy. The emission of radiation is a natural process for these elements, and it can be quite intense depending on the specific isotope and its half-life. The half-life of an element is the time it takes for half of a sample of the element to decay, and this can range from fractions of a second to billions of years. Now, let's delve into the top 5 most radioactive elements and understand what makes them so unique and hazardous. Francium, for instance, is extremely radioactive and is one of the rarest naturally occurring elements. It has a very short half-life, about 22 minutes for its most stable isotope, francium-223, resulting from its inordinate number of protons, 87. Its high atomic number creates an unstable nucleus that undergoes rapid decay. Francium's rarity and high radioactivity make it a subject of interest in scientific research, though its practical applications are limited due to its short half-life and the difficulty in obtaining it. Radium, another highly radioactive element, is found in uranium ore. Its isotopes, particularly radium-226, have long half-lives, over 1,600 years, but they undergo alpha decay, emitting significant radiation over prolonged periods. Radium's atomic number, 88, contributes to its radioactive properties due to a high neutron-to-proton ratio, causing instability. Radium was once used in luminous paints for watches, clocks, and instrument dials, but its use has been discontinued due to the health risks associated with its radioactivity. Polonium is known for its highly radioactive isotopes, notably polonium-210, which has a half-life of only 138 days. It undergoes alpha decay, releasing intense radiation that is harmful in minute quantities and was famously used in the assassination of Alexander Litvinenko. Polonium's ability to release a large amount of energy in the form of alpha particles makes it extremely dangerous, even in small amounts. This property has led to its use in anti-static devices and as a heat source in space satellites. Uranium, particularly uranium-238 and uranium-235, is naturally radioactive. These isotopes have long half-lives, over 4.4 billion years and 700 million years, respectively, and undergo alpha decay, leading to the release of radiation as uranium decays into various other elements in the actinide series. Uranium is widely known for its use as fuel in nuclear reactors and in the production of nuclear weapons. Its long half-life and the energy released during its decay make it a critical element in the field of nuclear energy. Thorium is radioactive and has a long half-life, about 14 billion years for thorium-232. It undergoes alpha decay and can produce uranium-233 when it captures neutrons. Thorium is used in some nuclear reactors because of its ability to breed fissile material, but its radioactivity arises from the inherent instability of its isotopes. Thorium's potential as a safer and more abundant alternative to uranium in nuclear reactors is being explored, though challenges remain in developing the technology to utilize it effectively. The primary driver behind the radioactivity of these elements is their atomic structure, which causes instability in their nuclei. The instability leads to various types of decay, alpha, beta, or gamma, releasing radiation in the process. These elements not only contribute to our understanding of nuclear physics, but also have applications and implications in energy, medicine, and radiation safety. Understanding the properties and behaviors of these radioactive elements is crucial for advancing technology and ensuring safety in their use. From powering spacecraft to treating cancer, the applications of radioactive elements are vast and varied, highlighting the importance of continued research and development in this field. Credits script by your name, voiceover by narrator's name.